Before we start, what is a high-performance liquid chromatography or known as HPLC? High-performance liquid chromatography is an analytical technique used to separate, identify, and quantify components in a mixture by passing it through a column pack with a stationary phase under high pressure with a liquid mobile phase carrying the sample. It is widely used in research for precise and efficient analysis, for example, chemistry, biochemistry, pharmaceutical, and more. The figure shows a bit of impression of how HPLC works overall and what it looks like. Let's move on to objective. What is the objective for this experiment? The first objective is to determine the retention time of a standard solution or known as caffeine. Second, it is to identify the caffeine peak in a soft drink sample. And lastly, it is to determine the amount of caffeine in a soft drink sample using a response factor method.
So for methodology, I'm going to talk about overview of HPLC for function. I'm going to expand this from A to F, which is on the screen. So first A, solvent delivery pump. It is to deliver the mobile phase at constant flow. What is mobile phase? Mobile phase is organic or aqueous solvent are used depending on analysis. B is degassing unit. It is used to remove dissolved air from the mobile phase. And C is injector. It is used to introduce standard solution or real sample to the HPLC column. So we're going to get the standard solution. It's from the sample vial, which is used to store standard solution or sample solution. Then we move to D, which is column oven. Column oven is used to keep the temperature constant. In the column oven, we have the column, which is used to separate each compound contained in the sample. Then we go to detector. Detector is used to detect the eluted compound from the column. Then we have the drain or workstation. The drain is used when the compound is not suitable for us to read, and the workstation is used as the signal from the detector is processed and the chromatogram is displayed.
The next video is going to show you how HPLC work.
High-performance liquid chromatography (HPLC) is an analytical technique used to separate, identify, and quantify components in a mixture. The process begins with the injection of a small liquid sample into the system, where it mixes with a liquid solvent known as the mobile phase. A pump pushes the mobile phase through the system at high pressure, carrying the sample into a column pack with a stationary phase. Inside the column, the sample components interact differently with the stationary phase based on their chemical properties, causing them to separate. Compounds with a stronger interaction move more slowly, while those with weaker interaction move faster. As the separate components exit the column, they pass through a detector that measures specific properties such as UV absorption or refractive index. The detector generates signals corresponding to the concentration of each compound, producing a chromatogram, which is a graph that displays retention time and signal intensity. Each peak of the chromatogram represents a specific compound, allowing for its identification and quantification by comparing retention times with known standards.
I will be explaining about the results. In this figure, it shows the chromatogram of caffeine. For caffeine, it showed a retention time of 2.482 minutes. The peak area for caffeine is 6249.48779. Next figure shows the chromatogram of Coke, which also contains caffeine. We only choose the peak that was similar to the peak that the standard had in the chromatogram in order to determine the caffeine concentration of Coke. In the chromatogram, Coke had a retention time of 2.481 minutes and a peak area of 700.12305. This figure shows the chromatogram of Levita. The peak that had caffeine in it had a retention time of 2.479 minutes. Its peak area, on the other hand, is 1.111511 times 10 to the power of 4. To sum it all up, the caffeine standard had a retention time of 2.482 minutes with the peak area of 6249.48779. In order to obtain the peak area of caffeine of the other samples, We compared the chromatograms of the soft drink samples with the chromatograph of the caffeine standard. The peak that was similar to the caffeine standard was taken, and we obtained the peak area of caffeine for each of the soft drink samples. The soft drink sample of Coke had a retention time of 2.481 minutes with a peak area of 7001.12305. The other soft drink sample of Levita had a retention time of 2.479 minutes and a peak area of caffeine of 1.1115 times 10 to the power of 4.
Now, for the calculation part, to determine the response factor for the caffeine standard, we begin by dividing the peak area of the caffeine standard by its known concentration. This calculation provides a measure of how the detector responds to a specific amount of caffeine. Using the peak area value obtained earlier and dividing it by the caffeine standard concentration of 1 mg per milliliter, we calculate the response factor. In this case, the response factor is determined to be 6,249.49 mg per milliliter, providing an essential reference point for subsequent calculations. Using the response factor that we obtained earlier, we can now calculate the concentration of caffeine in the unknown sample, which in this case is Coke. To do this, the peak area of the caffeine sample is divided by the response factor, yielding a concentration of 1.12 mg per milliliter. To express this value in ppm, we apply the conversion factor where 1 mg per milliliter is equivalent to 1000 ppm. As a result, the caffeine concentration in the sample is calculated to be 1120 ppm. The same method was applied to determine the caffeine concentration in the unknown sample, which is Levita. From the calculations, the concentration was found to be 1.78 mg per milliliter. Converting this value to ppm using the conversion factor where 1 mg per milliliter equals to 1000 ppm, we obtain a caffeine concentration of 1780 ppm. For discussion, the caffeine standard solution with a retention time of 2.48 minutes represents the time required for the compound to travel from the injection port to the detector. The caffeine peaks in Levita and Coke are identified by matching their retention times with the standard, measured at 2.479 minutes for Levita and 2.481 minutes for Coke respectively. Levita, with a peak area of 1.112 10 to the power of 4, contains a caffeine concentration of 1780 ppm, while Coke, with a peak area of 7001.12, has a concentration of 1120 ppm. These results clearly reveal that Levita has a significantly higher caffeine content than Coke.
So, in conclusion, we are able to achieve the experiment's objective by determining the retention time of the standard caffeine solution, which is 2.482 minutes. The caffeine peaks in Levita, which is 2.479 minutes, and Coke is 2.481 minutes, were identified. Using the factor method, the caffeine content was calculated as 1780 ppm for Levita and 1120 ppm for Coke.